In the previous section, we talked about measurements and how important measurements are in science. And we also talked about units. So for example, in the first one, we have 212 grams. We instantly know this is a measurement of mass because it has a unit of grams. In the next case, we have 41.8 milliliters, which we know is a measurement of volume because it has a unit of milliliters. The next thing we need to talk about is significant figures and measurements. And sometimes these are referred to by students as kind of a pain in the butt and annoying and this kind of stuff. But the truth of the matter is they are very, very important. So when we look at significant figures, essentially what we're looking at is some rules that tell us how many significant figures are in a measurement. So for example, if we use a ruler, a metric ruler, to measure something, we might be able to figure out the measurement to the nearest maybe tenth of a millimeter, for example. However, if we use a sophisticated laser, like it's inside of an IR instrument, for example, it can measure distance far more accurately than to the nearest tenth of a millimeter. So it depends on the device we use for the accuracy in our measurement and whether a digit in a measurement is significant or just nonsense. And we'll take a look at that in a few minutes. But before we do that, let's talk about what significant figures are. And also the rules for zeros, because the rules for zeros are what are the most complex, because zeros can be placeholders. So the first thing to know about significant figures is all new non-zero numbers in a measurement are significant. So if we look at the example 212 grams, this has three significant figures. None of them are zero, so they're all significant. If we look at 41.8 milliliters, this also has three significant figures because, again, none of them are zero. However, zeros are a different case. Zeros are significant if they are between two significant figures, which I realize I have no examples of that now, so I'm simply going to just add a zero in the middle here to change that. So, and zeros are also significant if they are after a significant figure and a decimal point. Order, this should say, I don't know why it was like that. Order of the sig fig and decimal point doesn't matter, i.e. they are not placeholders. So if a zero is after both a significant figure and a decimal point, whether or not the sig fig comes first or the decimal point comes first, that doesn't matter, then the zero is not a placeholder and therefore it is significant. The best way to explain this is in terms of examples. So if we look at these zeros here, first of all, this is kind of a cosmetic zero. So this zero is never significant. But then we have 0.00201. And we're looking for the significant figures in this data. Well, these zeros are after a decimal place, but they're not after a significant figure. So they are not significant. This zero in the middle here is sandwiched between two significant figures, namely the 2 and the 1. So this zero is significant. These two zeros are not significant, they're just placeholders, so therefore they're insignificant. They're not after a number and a decimal place. So this has three significant figures highlighted before, the 2, 0, and the 1. Let's look at the next example. We have 0.87500. This zero is not significant, just because it's kind of cosmetic. We use it when we write numbers in typing, like in here. And we also have 87500. So what about these zeros? They're after a decimal place, and they're after some sig figs, namely the 8, 7, and 5. So these zeros are significant. They are not placeholders. So all of these are significant. 1, 2, 3, 4, 5. So this has 5 significant figures. Let's look at another example. 18.20. In the previous case, the decimal place came first, then some numbers, then the 0. In this case, some numbers come first, then a decimal place, and then a 0. That doesn't matter. This 0 is after a decimal place and a sig fig. It is not a placeholder, it is significant. So in this case, all 4 are significant. The last case is a little bit strange. Technically speaking, these zeros and the number 5,000 are not after a sig fig and a decimal place. Specifically, they are after, there is no decimal point. So they're after a number, but there's no decimal point. So that is not clear. This is kind of an ambiguous case. So it's not real clear how many significant figures that there are. One way to fix this would be to put it in scientific notation. If you wrote 5.000 times 10 to the 3, that would clearly be 4 significant figures. If you wrote 5.0 times 10 to the 3, that would clearly be 2 significant figures. One thing that ALEKS does, which you will use for your homework, is it uses a decimal point at the end. And if it says that if you put a decimal point here, this now becomes 4 significant figures. So that rule is used by some people, but not by others, and you do need to use it for the ALEKS program. However, this is kind of ambiguous, and I would suggest using scientific notation to fix it. What about if we're actually making a measurement with significant figures? Well, let's say that we want to measure the length of this yellow line. I was trying to make it so you could measure the length of an object, and it turns out it was difficult to draw an object and not take out the graduations. So we're just going to measure how long this yellow line is, or assume the object we're trying to measure comes to right here. The first thing we need to do is we need to figure out the values of these unnumbered graduations. And often we take this for granted, but it is important that we be able to figure it out. A lot of times they're tenths or ones or something like this, and they're fairly straightforward. But other times they're not. In some devices you'll use in the lab, like a graduated cylinder, they might be 0.2 milliliters. So we do actually need to figure it out. So how do we figure that out? Well, the first thing you do is you take the distance between the numbered graduations. In this case, the distance between 1 and 2 in centimeters is 1 centimeter. And then you count how many graduations are in between. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 graduations in between. If this distance is 1 centimeter and there are 10 graduations in between, each one of these is 0.1 centimeters. 1.1, 1.2, 1.3, so on and so forth. Here I've labeled them in the 2 range. So this is 2.1, 2.2, 2.3, 2.4, 2.5, and so on. So the question still is up in the air. Now that we know the graduations, we know it's between 2.2 and 2.3, well, how do we decide how many decimal places we should have? Should it be 2 centimeters? Well, this one's kind of obvious. It's clearly more than 2 centimeters. Should it be 2.2 centimeters? Probably not, because the yellow line isn't on the 2.2 centimeters. Should it be 2.27 centimeters? Because it's closer to 2.3 than it is to 2.2. Yeah, this probably seems reasonable. What about 2.275? Maybe it's a little closer to 2.8 than it is to 2.7. Or as an extreme case, what about 2.275642345, whatever, all these digits? This is clearly ridiculous. This is the equivalent of using the laser device that I mentioned before, and we're not using a laser measuring device. We are simply using a ruler, in this case, to measure the distance. So there's a rule. The rule is 1 estimated digit. Make measurements with 1 estimated digit. So we are sure of 2.2 because we know it's between 2.2 and 2.3. So now we need to make 1 and only 1 estimated digit. I'm going to estimate that this is around 7. You might see it as 2.28, but I'm going to call it 2.27 centimeters. It is estimated. We might get slightly different values. Now you wouldn't want to call it 2.21, for example, but you could call it 2.28, and that's totally fine. And don't forget your units. We also want to include the units. So the best answer here is actually this one. 2.27 centimeters. This has too many significant figures. This is just ridiculously too many significant figures, and these two have too few significant figures based on the measuring device. One other thing to note is that we're often measuring volumes in the lab. So measuring volumes in the lab will be done in a very similar way to what was just described. We will also measure masses in the lab using balances. Balances these days are digital, so the instrument manufacturer has already taken this into account. Said another way, if you're making a measurement on a balance, simply write down all the digits that a balance gives you. In our labs, we typically use 4 decimal place balances, but you can get ones with more or less decimal places. essentially depending on how much money you want to spend on it. And what you want to do is simply write down all the decimals available to you when you use a balance in the lab. But you will also measure volumes, and volumes aren't digital. Volumes aren't measured digitally, they're measured in this analog, if you will, way. So let's say that we want to measure this volume right here. And I've done the graduations down here because they didn't fit in well with this black box here showing that we're zooming in. So let's go ahead and do this. The first thing is we want to find the value of each graduation. So we need to look for the distance between the two lines. So the distance between here and here in milliliters is 5. 10 to 15 is 5 milliliters. How many graduations are there? 1, 2, 3, 4, 5. 5 milliliters divided by 5 graduations equals 1 milliliter per graduation, meaning this is 11, 12, 13, 14, 15. Or up here, 21, 22. So the volume is between 21 and 22 milliliters. Now, a weird thing happens when you're measuring the volume in a graduated cylinder that doesn't happen when you're measuring the length of a pen or whatever, some solid object. You get this thing called a meniscus. This occurs because water sticks to glass more than it sticks to itself. So near the edge of the glass, it's higher, and where there's less glass in the middle, it's lower, and you end up with this thing called a meniscus. Chemists have decided that we read volumes from the bottom of the meniscus. So we know that this volume is between 21 milliliters and 22 milliliters. So we now need to estimate a digit. To me, it looks like it's more than 21 and a half milliliters. It looks like it's a little closer to 22 than it is to 21. No, this is 20. So this is 21, this is 22. It looks to me like it's a little bit closer to 22 than it is to 21. So I'm going to call this 21, those are the digits I'm sure of, 0.6, and I don't want to forget my units, milliliters. So this is the volume of this particular liquid in the graduated cylinder, water. It is worth noting that not all numbers are measurements. So these are some numbers that are not measurements. Numbers that are not measurements do not have significant figures. And an example of this is counted numbers. So for example, if we measure the mass of 6 pennies, it's exactly 6 pennies. We literally count up to 6 pennies. There's no error in that. There's no accuracy or imprecision. It's exactly 6 pennies, or the volume of 25 M&Ms. Okay, there's exactly 25 M&Ms. There's no uncertainty in that. Another thing that seems like it's a measurement because it has units are defined equalities. 1,000 grams is exactly 1 kilogram. There's no uncertainty in this, so this does not have significant figures. Another example of this is 1 atmosphere equals 760 torr. These are pressure units. We could go on with defined equalities in the metric system. However, one thing to remember is these do not count towards significant figures because they're not measurements, they're definitions. These two things are exactly the same. 1,000 grams is exactly 1 kilogram. No uncertainty there. So therefore, no significant figures. One other thing that we need to talk about is the difference between accuracy and precision. And I've mentioned these terms before, and they're often used interchangeably, but they are not the exact same thing. And one of the best ways to describe accuracy and precision is using a bullseye. So in a bullseye, the goal is to hit the center. So accurate throws are ones which are exactly in the center of the bullseye. So if you get them exactly in the middle, they are accurate. They are precise if they are close to one another. So if this is 3 throws or shots or whatever, this is both accurate and precise. It's accurate because it's near the middle. It's precise because it's close to each other. If we look at these 3 examples, they're not near the middle, but they're near each other. So these values are precise because they're close to each other, they're reproducible, but they're not accurate because they're not near the middle. And in this last case, the values aren't really close to each other, and they're not close to the middle. These are not accurate and not precise. In terms of a bullseye, this is pretty straightforward. But let's think about it in terms of data as well. If we measure scientific data that's accurate, it means it's close to the accepted value. And precise means that if I repeat the experiment multiple times, I get the same value over and over and over again. So precision is reproducibility, accuracy is close to the known or the accepted value. This is common in scientific endeavors. We get data that is reproducible, but it is not what we expect to get. And there are two major reasons for this. One reason is there's some type of systematic error, like say the balance is acting funny. I mean, that's not a common one, but it's certainly possible. So the balance is acting funny and it's consistently measuring lower than it should. So in that case, we would get reproducible data, but it wouldn't be what we expected. This could also be due to the fact that the bullseye, the accepted value, isn't actually correct. And the bullseye really should be over here. And we've discovered something new that changes how we think about the experiment. This data is a scientist's worst nightmare. It's not accurate and it's not precise. So we do an experiment, we don't get what we expect, so it's not accurate. And if we do it again, we get something completely different. All right, this is the kind of data that gives scientists nightmares. So these are the differences between accuracy and precision. This is just another example of that. These data are probably relatively accurate. Okay, accuracy and precision are relative terms, but they're not very precise because they're not very reproducible. You could also make an argument that these aren't accurate or precise. This data, or these shots, are precise, but boy, they're not accurate. They didn't even hit the bullseye, much less in the middle of the bullseye. And these two cases, Archer Y and Archer Z, are not accurate and not precise. They're all over the place and they're not near the middle. So this is, again, every scientist's nightmare when it comes to data. The next thing we need to do is we need to talk a little bit about how do we use significant figures when we do calculations. It's very common in science to measure multiple things and then do calculations with the multiple measurements. And previously, we looked at the calculation of density. And in just a couple minutes, we'll do another calculation of density using some measured data. So there are some general rules for significant figures in calculations. The general rule, which is not very helpful, but just to give you an idea of where we're going, is the significant figures in the result of the calculation should approximate the accuracy of the least accurate measurement. So for example, if we are measuring density and we have a balance which has 6 decimal places, and we measure the volume in a graduated cylinder which only has, depending on the size, 1 decimal place, then we have to give the result for our density based on the inaccurate volume measurement, not on the super accurate mass measurement. So that's the general rule. So basically, it limits us. We're limited by our least accurate measurement. But there are some specific rules, and they apply to adding and subtracting and multiplying and dividing. So for adding and subtracting measurements, the result of the calculation should have the same number of decimal places as the measurement with the least number of decimal places used in the calculation. So when we're adding and subtracting, we care about decimal places. When we're multiplying and dividing, the result of the calculation should have the same number of significant figures as the measurement with the least number of significant figures used in the calculation. So there are slightly different rules depending on whether we're adding and subtracting or multiplying and dividing. And one important thing that I need to tell you is that your calculator will lie to you. Your calculator, Excel, these things do not do significant figures properly. Now, there may be a calculator out there that does, but generally speaking, calculators are not very good at this. So the number that is displayed on your calculator will occasionally by chance have the correct number of significant figures, but most of the time it doesn't. So let's look at a couple of examples. Let's say that we were trying to find the area, the square meters of whatever this is. This whatever area is 2.11 meters on one side and 4.8724 meters on the other. When you multiply these two numbers in the calculator, this is what you get. However, this doesn't have the proper number of sig figs. Notice that we multiplied, so we have to use the multiply and divide rule. We want our answer to have the same number of sig figs as the number used with the least number of sig figs. So this one has 3 significant figures, and this one has 1, 2, 3, 4, 5 significant figures. Since this one has 5 and this one has 3, obviously 3 is less, so our answer should have 3 significant figures, which in this case is 10 point. This is the digit we care about. Since this is an 8, or it's 5 or more, we round up. So we put 10.3, and we want to put our units, I'm just going to do this way, 10.3 meters squared. So this is the best answer for this one. Let's look at the next one. In the next case, we have 14.2 grams plus 8 grams. So we're clearly adding two masses together. When you type this into a calculator, you get 22.2 grams. However, the rule is, since we added, the number of decimal places. This has 1 decimal place. This has no decimal places. So our answer should match the least. No decimal places is, of course, greater than 1 decimal place. So our answer should have no decimal places, which is 22 grams. And when you're adding, you just use the same unit. Let's look at another example. In this case, the person was calculating density. They found that the mass of the object was 29.6854 grams, and the volume of the object, or the solution or whatever it was 25 milliliters. So they take the mass and they divide by the volume, and they find this in the calculator. Since we're dividing, we care about the total number of sig figs. This has 1, 2, 3, 4, 5, 6 significant figures. This has 1, 2, this counts, 3, because the 0 is after a number and a decimal place. So this is 3 significant figures, which means our answer should have 3 significant figures. This is the digit we care about, 1, 2, 3. Since this is a 7, we do have to round up, and we get 1.119 grams per milliliter. Oops, milliliter. Yes, if I could type that in properly, it would be good. All right, in the last case, we're doing a subtraction. We have 8.7851 grams minus 8.22 grams. Since we're subtracting, we care about decimal places. This has 4 decimal places. This has 2 decimal places. So we want our answer to have 2 decimal places. Since this is a 6, since this is a 5, we want to round the 6 up. So in this case, it's 0.57 grams is the result of this subtraction with 2 decimal places. Notice that if I were to use the rules for multiplying and dividing in this case, I would get the wrong answer, because this has 1, 2, 3, 4, 5 total sig figs, and this has 3, but my answer only has 2 sig figs. So when you're subtracting, you can actually lose significant figures because it goes by decimal places and not by significant figures. You will use these rules quite often when you're doing calculations in this course, so it's a good idea to become familiar with them. As an example, I would like to go through a problem where we determine the density of this piece of rebar. So basically, for this piece of rebar, we put it on a 3 decimal place balance, and we found that its mass was 69.658 grams. And then we had this much water in a graduated cylinder. We dropped in the piece of rebar into the graduated cylinder, and the water went up. So essentially, we want to find the volume of this piece of rebar by displacement. So the first thing we need to do is find this volume, and find this volume, and then subtract this volume minus this volume, and we can find the volume of the rebar. And then you recall that density equals mass divided by volume, so then we can determine the density, and we're going to do so with the correct number of significant figures. So this is kind of combining ideas. These are actual measurements that one could make in the lab. Obviously, this is an example, but they are measurements that one could make in a lab where significant figures play a role, because the mass and the volume don't have the same number of sig figs, as you will see. So first thing we need to do is we need to figure out the value of each one of these lines. Well, the distance between the measured numbers is 5 milliliters, and there are 5 graduations, 1, 2, 3, 4, 5, which means that each graduation is 1 ml. So this is 11, 12, 13, 14, 15. And I have put the bottom of the meniscus with a red pen here, just so you could see it. When I printed this, you couldn't really see it that well on the camera, so I just colored it over in red. So in this case, the bottom of the meniscus is between 13 and 14 milliliters. And to me, it looks like it's right in the middle. So I'm sure about the 13, and now I need to estimate the next digit, and to me it looks like it's right in the middle, so I'm going to call it 13.5 milliliters. Repeat the same thing for up here. Note that the graduations are the same, so this is 21, 22, and 23 milliliters. In this case, I'm between 22 and 23 milliliters, so I'm sure that it's 22 milliliters. Now I want to estimate a digit. In this case, to me, it looks like it's a little bit closer to 22 than it is to 23, so I'm going to call this 22.4 milliliters. So now I've found my two volumes. So the amount that this volume of water went up is exactly equal to the volume of this piece of rebar. So volume of the rebar equals 22.4 milliliters minus 13.5 milliliters, which is equal to 8.9 milliliters. Now, this is what I would get for the calculator, from the calculator. Let's see if the sig figs are right. I'm subtracting, so therefore, I want to use the least number of decimal place. 1 decimal place, 1 decimal place, 1 decimal place. So I'm going to simply just underline that to show that that's the significant figure. Note that this, if this, it wouldn't, but if this somehow miraculously came out to 8.87234441 or whatever on the calculator, you would want to keep all those digits for the next calculation, but you just want to underline the digit that is significant so that you can then use that to calculate the significant figures of your final answer. Now, I have the volume of this piece of rebar, 8.9 milliliters, and it's two significant figures because that's the sig fig. Now I want to do the division. The mass of this piece of rebar is 69.658 grams, which was measured on a balance, obviously not by us. This is just an example, but you could do this in the lab. You can measure that on the balance. And the volume is 8.9 milliliters, where that's the sig fig. When we do this out, we find on a calculator that it's 7.826746 and a bunch more numbers. Now, we need to answer this with the correct number of significant figures. So, now we're dividing. So it's the total number of significant figures that matter. So we have 1, 2, 3, 4, 5 sig figs in our mass and 1, 2 sig figs in our volume. So our answer has to have the least number of significant figures, which is 2 significant figures, which is this one right here. So we want to, since this is a 2, keep it the same, 7.8, and then include our units, grams per milliliter. So in this case, to sum up, we figured out the density of this piece of rebar by displacement, by finding the initial volume and the final volume, putting the object in the water with the object of known mass in the water, and seeing how much water was displaced. We also had to keep track of our significant figures throughout this process in order to determine the density with the correct number of significant figures.